Hello everyone, my name is Akash and my group members Ashish, Pratmesh, Sagar are going to talk about speech signal analysis using digital filters in the subject called digital signal processing. So how the speech signal is analyzed using digital filters we are going to see. First of all, the introduction, what was the literature review, what we all need to study about this, research design and the research questions, how we have collected the data and processed it, what was the main methodology, and the MATLAB implementation, how we have implemented in MATLAB, and what were the findings and the final conclusion. First of all, a speech signal is very important way of transferring message, and for the better communication we need a smooth and a clear signal. So for a smooth and clear signal we have to remove the unwanted noisy signal. So for that we have to process that speech signal. In speech signal processing, we use filters for that to remove the unwanted noise present in that signal. The filters can be analog and digital, but in digital signal processing we mainly use uh, digital filters because they are capable of performing the specifications very efficiently and in a better way. So in this we have designed and implemented FIR filters and IIR digital filters using multi-rate signal processing. For literature review, we have done we have researched about three papers. First was the comparative analysis of speech signal, in which there were different windowing methods: Hamming, Henning, and Blackman window. Second was the low bitrate speech coder. Uh, in this, we have studied that how the speech signal is uh, subdivided into its subband. And in third, again the windowing techniques and its comparison they have done between the Hamming, Henning and Blackman window using the phase frequency response, phase response. So what we have to need to study before this topic mainly is the digital filters. You should know about what are the digital filters, how they are how they are used, and why. So the main and the basic role of digital filter is to remove the unwanted signal present in the uh, speech signal which you are processing. So for improvising the communication system, we need to know how the signal is processed and how the digital filters are applied. So in the further slides, we are going to see how these filters are applied. And for research design, what was the main uh, design behind this topic is that first of all we have taken one noisy signal, we have divided it into frequency subbands by downsampling it, and various transforms are applied to that signal like fast Fourier transform and FWST, and then and pass through the digital filters which are FIR filters and IR filters. In that FIR filters the various windowing techniques were there, and IR filters by using Butterworth and Chebyshev. Finally, we have done the quantization on the filter coefficients of the signal, and then performance of digital filters were measured by calculating the signal to quantization noise ratio. By this ratio, we can conclude that which filtering technique is best and which digital filter is best suited for a speech signal and why. So these are the research questions. The data collection is done from the TIMIT database. In that data, we have taken one audio signal. There are various thousands of audio signals present in that audio recorded audio signals. So from that we have taken one audio file which is a .wav file extension, and then the what was the main methodology is that we have taken that speech signal, then we have added the Gaussian noise to make it little bit more noisy. Then this noisy signal is downsampled into multiple sampling rates into subbands like subband 1, 2, 3, and so on. Then various transforms are applied to this like fast Fourier transform, fast Walsh-Hadamard transform, and discrete wavelet transform. Then we have designed the filters and implemented it and applied on this noisy signal. For in FIR filters, various windowing techniques are applied like rectangular, Hamming, Blackman, and Casio. And in IIR is designed using Butterworth and Chebyshev. Then after this, we have done the quantization, and finally the signal to noise ratio is compared. This was a basic block diagram which you can imagine what all is happening. Like first of all we are taking the signal, adding the noise, then downsampling it, then applying the various transforms, then designing the filters and implementing on that, and we are comparing the final output, the performance of the filters without quantization also and with quantization too. Yeah, on the based of SQNR, with that is signal to quantization ratio. So the final MATLAB implementation I will show you in the MATLAB. I have included the output in the further slides also, but here we can see the main implementation of MATLAB. I will run it once again. So here basically we are reading the audio signal which I told that I have taken it from the TIMIT database in a .wav extension. We are reading it and plotting the signal. So it looks like somewhat this, the original speech signal. Then we have added the Gaussian noise to it of power 10. This is the output of the noisy speech signal. Here the noise is added, and this is the without the noise. So then we have downsampled the noisy signal by the factor of 2, in, that is subband 1, again by factor of 2, that is subband 2, and so on, the subband 3 and subband 4. Then we have applied the fast Fourier transform on this noisy signal, whose output is this, using the command FFT and plotting the graph. Then this fast Fourier transform is applied to their downsampled subbands also, whose output you can see here. Then after the fast Fourier transform, we have designed the filters which are IIR and FIR. In IIR filters, there are two main, Butterworth and Chebyshev. And in Butterworth and Chebyshev, we have done low pass and high pass. So in Butterworth, this is the high pass filter and this is the low pass. And for Chebyshev, Here you can see the high pass one and here the low pass. So here we can compare also the Butterworth filter and Chebyshev filter. Later on I will tell you what is the main difference and which is more preferable. Then after the IR filters we have designed, here you can see we have applied the Butterworth filter to its subband also, which was not necessary, but for better understanding and for the performance of the filters we have done that. Now the FIR filters are designed by the various windowing techniques: Hamming window, Henning window, Blackman, rectangular, and Casio. And in that we have done high pass and low pass too. So this was the high pass Blackman filter, low pass Blackman, high pass rectangular, low pass rectangular, and then the high pass Blackman, low pass Blackman, and finally the Cashier one. So these were the filtering techniques we have done. Now we will back to the final PPT. Here I have included all the outputs and codes, reading the speech signal, adding the Gaussian noise, downsampling the signals into subbands, then applying the fast Fourier transform, FFT on the downsampled subbands also, in the filter design of Butterworth high pass filter, low pass Butterworth filter, high pass Chebyshev filter, low pass Chebyshev filter, and applying the various windowing techniques for FI filter, Hamming, Henning, Blackman, rectangle, and Cashier. So after all this implementation and processing the speech signal, we have some findings, like the Blackman high pass filter provides high signal to quantization noise ratio than their windowing techniques. And the second one is Chebyshev high pass filter provides high SQNR than other techniques which was Butterworth. So the final conclusion is that FI filter is very complex and costly as the order of the filter is very high. So we prefer IR filters, which is very efficient also. And among the IR filters, that is Chebyshev and Butterworth, Chebyshev filter is very efficient and gives the sharp response as compared to Butterworth. So Chebyshev is preferable than Butterworth. These were the selected references which we have taken for the three research papers which we have studied earlier. So thank you.